So we've looked at dealing with composite functions where the inside is a linear function. And what I want to look at here is actually a process where we can handle composite functions where the inside is not a linear function. Okay, now it will work also for the ones that have linear functions inside. And actually that's why we were able to simply use that 1 over a idea in the previous in our previous lesson. But I want to show you what we're doing here, okay? If I have some integral, okay? Let's say I have some integral that I'm trying to find, and it's the integral of a composite function, like f of g of x dx, okay? This is what we were dealing with before, but g of x was always linear. Well, I can actually substitute out and make this, instead of another function, I can simply change the variable that I'm dealing with, okay? And this is kind of an equivalent to a chain rule. It's not really a rule, it's a process, okay? But let's look closely at what's going on here. Notice I have u that is a function of x. So that's why, we see here that u is g of x. Okay? What this process says is that if I have the integral of f of some function u, there's my composite function, times the derivative of u with respect to x, dx, then I can integrate that as f of u du. Now notice we changed variables from x to u. Okay? All right, so let's look at how this is broken down. Okay? We have this function f of some function u, all right? I'm going to go through this kind of quickly. I think once we do a couple examples, this thing will make a lot more sense. It's a little bit jumbled right now. But if I take u, which is g of x, and I take the derivative, okay? The derivative of u with respect to x is du dx. That's the same as g prime of x. Okay? So now if I took this equation right here, and I solved it for du. I multiplied by dx on both sides. Then du is g prime of x dx. Okay? Now, notice here, I used a basic power function. I wrote some function g of x to the r power times g prime of x dx. And notice here, g of x is going to be u, so I'm going to replace that with u. And this whole thing is du. So I'm replacing this with du. And you say, well, what in the world? Why would I bother doing all of that? Well, this is why right here. What's the integral of something to the r power?
It's like the inverse of r plus 1.
U to the r plus 1
over r plus 1.
Over r plus 1. So I do that, and then I didn't want my answer in terms of u. I wanted my answer in terms of x. So now I can plug back in that g of x to the r plus 1 over r plus 1. Okay? So notice we're substituting out something to make it look a little bit simpler, then we take the integral, then we plug that thing back in. And if you think about it, this is kind of the thing that we did back when we looked at the quadratic formula, and we saw ones that weren't quadratics, but they were in a quadratic form. Okay, let me illustrate over here. Remember when we did equations kind of like, you know, x to the 6th plus 5x cubed minus 7 equals 0. And we wanted to solve for x. Okay, well, and we could use the quadratic formula because this power was twice as much as this power was. So what we did in our heads is we said, okay, I'm gonna let y equal x cubed. And I'm gonna treat this equation as y squared plus 5y minus 7 equals 0. And then you did the quadratic formula, right? Okay? So we've done this kind of a thing before, but remember at the end of this, after you did y equals negative 5 plus or minus square root of 25 plus 28 all over 2, you weren't done. Because we didn't care what y equaled, we cared what x equaled. So then you took that answer, and that was x cubed, so x, you had to take the cube root of your answers. And I don't know what those are totally, so that's square root of 53 over 2. So you had to take the cube root and finish solving for x. So the process we're doing here with our integral is kind of similar to this. We are simplifying how it looks so that we can use methods that we've learned before. Then we have to substitute back in to get our final answer. Okay? Now, let's illustrate this with something that we are familiar with. Okay? We've done integrals like this already. Okay? Now, let's do this the way that we were doing it in the last section, and then I'm going to do it in the way using this method. Okay? So, in the last section, I'll do it down here. If I were doing this integral, I would have pulled the 2 out. 2 integral of 2x minus 1 cubed dx. And then when I take the integral, it's 2 times. And then remember, since this was linear, we did the 1 over a times the antiderivative, right? So, so what would we have done? What would we have gotten here?
One-fourth.
What's our 1 over a?
1 over a is 1/2.
1/2. And then what's the integral of something cubed?
1/4.
Fourth over 4.
Yeah, okay. So I'd put the 2x minus 1 to the 4th all over 4. Okay? Notice here the 2 and the half cancel out. And I have a 2x minus 1 to the 4th over 4 plus c. Okay? Now, here's the cool thing. I'm going to get the same answer. I'm just going to get to the answer a slightly different way. Okay? Now, I will tell you that this method here, when you've got a linear function inside, is slightly faster. And in some cases, it's a lot faster. But it is a little bit faster. But let's take a look at what we're doing here, okay? What is the inside function?
2x minus 1.
The 2x minus 1. Alright, so that's 2x minus 1. The inside function right here. Now, what is du dx?
2.
It's 2. Okay? So now, if I take that equation that I just got here, and I solve it for du, what am I going to have? Du equals... No, we're overthinking right now. Du, it's what?
2x
Not 2x.
plus e.
I'm not integrating here, I'm just solving this equals 2. So what does du equal? 2dx. There you go. 2dx. Alright? Now, that's my du. Notice up here, I have a 2 and I have a dx. Alright, so I'm going to rewrite this integral as the integral of 2x minus 1 cubed times 2 dx. And then I can see very clearly here, I have the integral of u to the third du. Okay? There's the du. I'm replacing it with just a du. Okay? Here was our u. I'm actually substituting in a u. Okay? Is everyone with me here?
So you get the du because we said that the 2 dx is what du equals.
Correct.
And the 2 dx came from setting du dx is equal to 2, and then you just brought the dx over.
Mm-hmm. So now we can take the integral. The integral of something to the third is something to the fourth over 4, right? But I don't want the integral with respect to u, I want the integral with respect to x. So now I'm going to substitute back in the u. U is 2x minus 1. That's to the fourth over 4 plus c. Okay? All right. So here we're subbing in u, and from here to here we're subbing in 4u. Okay? Okay? That's the process here, and I know I'm going really, really slow. Once you get the hang of this though, this actually can go pretty quickly. Okay? The nice thing for you guys is we don't get too deep into this. In other words, the ones that you're going to have are going to be relatively set up for you. You may have to do a little bit of work to get it to look exactly right, but not a ton. Okay? Not a whole lot of work. All right? Let's look at another example. All right, so here's another one, and here's kind of a procedure that we could go along with it. Okay? Now notice this one actually has what we call a definite integral. So it has the 2 and the 5. So in this case, we're actually doing the integral from 2 to 5. Now we haven't learned how to do that yet. Okay? So for right now, I'm actually going to just write over that, okay? But this will work with definite integrals. and we have the fundamental theorem of calculus that we're going to learn in order to solve these, okay? But let's step through this process. What's u?
X plus 3.
X plus 3. What's the derivative of u?
That's
1.
the square root of x plus 3.
No, we don't want the square root right now. What's the derivative of x plus 3?
1.
Oh, that's.
It's 1. So du dx is 1. So what does du equal?
Dx.
Yes.
It equals d1 dx. Yeah, okay. So we can get rid of that. And it's 1 dx. We're multiplying by dx on both sides. All right, well, look at this. We already have a 1 dx in there. Okay? So that right there is du. And I can rewrite this now as the square root of u du. Okay? What's the integral of u to the 1/2?
Yeah.
U n plus 1 over n plus 1 times 1/2. Oh, based on the following again.
Okay, so if it's to the 1/2 power, it would be u to the
3 halves.
3 halves.
Or no, yeah.
The 3 halves. This will be.
Times 2/3.
times 2/3. That's right. Okay, divided by 3/2 is times 2/3. But I don't want to leave my answer in terms of u, so I am going to substitute back in 2 times x plus 3 to the 3/2.
Don't you have to keep the du with it?
Well, no, remember the du is what is telling us what to integrate with respect to. Like when we did the integral of x squared dx, it was just x cubed over 3.
Right.
There's no dx left anymore.
I get that it's just saying, like, the respect to, then do you just change it to du just for consistency's sake?
Well, yeah, and because that's what gets rid of other
Things.
parts in the function as we look at some that are a little more complicated than just these linear ones. That's what those things will go away then as a result. Okay. All right. For example, here's one that's a little more complicated. All right. We have the integral of x squared plus 3x to the 4th times 2x plus 3 dx. Okay? Now, what do you think u is going to be in this case?
There's 2, or no, it'll be x squared plus 3x, because there's a power.
Okay, then that's really good thinking there. We have two different things. We have a 2x plus 3 and we have an x squared plus 3x. But think about which one of those is inside of another function. The x squared plus 3x is being raised to the 4th power. So I'm going to try making that the u. U is x squared plus 3x. Okay? Now, du dx is what? What's the derivative?
2x
Plus
plus
3.
3.
Yeah. Oh, what do you know? That looks familiar.
What? It's linear.
So then,
Well, the original one wasn't linear. The derivative happens to be linear, so... But watch what happens here. If I solve for du,
2x plus 3.
I have 2x plus 3 times dx.
Oh.
And look at this. That matches that. So this whole thing the 2x plus 3 dx, I'm going to substitute out and substitute in du.
That's crazy.
Also, I have u is x squared plus 3x. I'm going to substitute that out and make this the integral of u to the 4th du. Okay? Now, we all know how to take the integral of u to the 4th. That's just u to the 5th over 5. So you see how we took something that looked really complicated at first, and until we had this method, we would have to expand out the x squared plus 3x to the 4th, and then FOIL in the 2x plus 3. But we don't have to do that, because this one matched up to where we could do u substitution, we sub it out, so we have something simple like a u to the 4th du. We take the integral now, and now all we have to do is substitute back in the u. So this is x squared plus 3x to the 5th over 5 plus c. Okay? So again, we look for the inner function x squared plus 3x. We take the derivative of that, and we figure out what du is. We look at the rest of the function that we're trying to take the integral of, and we recognize, hey, our du matches up with the other stuff that's left in the integral. So I can replace that 2x plus 3 dx with just a du. I can replace the x squared plus 3x with the u, and now I have something that I'm actually able to integrate. U to the 5th over 5. Then I just substitute back in the u, and I have my final answer. Okay? Now, another way of viewing this, and this I had never seen anyone do until kind of recently, but it might help you. Alright, so if you're a little bit confused, this might make a little more sense to you. If I were to do this alternative, back when I had du is 2x plus 3 dx. If I actually solve for dx, watch this. Dx is du over 2x plus 3. Sometimes what messes people up is they're wondering, where'd that 2x plus 3 go? Okay? Well, this is actually kind of what's happening, all right? If I were to rewrite this as the integral of u to the 4th times 2x plus 3 dx, well, dx is du divided by 2x plus 3. They cancel out, all right? I had never seen anyone do this until recently, and I was like, oh, that might be really helpful. That cancels out, and notice now we just have the integral of u to the 4th du. Okay? So it's kind of another way of getting to this step up here. But if it makes a little more sense to you, that might be worth doing that way. Okay? If that doesn't make any sense and the first way makes sense, then stick with the first way. Okay? The first way is the way I will typically do it, but just because that's out of habit. But if the other way makes sense to you, then go for it. Okay? All right. Okay, now, I told you that for the most part, what we're going to be dealing with are simpler ones where it's pretty much set up for you, okay? This is about the extent to which we're going to take this, all right? In AP Calculus, we get into even deeper ones that are a little bit more, there's a little bit more to them. I might show you one of those just to maybe help you appreciate the fact that we're going to stop at this point. Okay, but if I were taking the integral of x squared over the square root of x cubed plus 5 dx, what would you say is u? Yeah, u is x cubed plus 5. And what would that mean we have for du?
3x squared.
3x squared and times dx, because it would be du over dx and multiplied by dx on both sides. Okay? You can just kind of get into that habit. When you do du, just take the derivative dx. Okay? Now, I want to rewrite this a little bit. Okay? I want to rewrite this integral. This x cubed plus 5 square rooted in the denominator is, I could rewrite as x cubed plus 5 to the negative 1/2, right? You guys can see that. And then the other part is going to be times x squared dx. Now, can I substitute du in? No. I'm missing a bit. The nice thing is, though, all I'm missing is the constant. Okay? I'm missing that 3. Okay? I'm missing the 3. So, let's remind ourselves of a rule that we learned before. Okay? If I have the integral of a constant times a function, I can take that constant out of the integral, right? We know that. We use that every time we do something like the integral of 2x cubed, and we just do the x cubed and normal, that's x to the 4th over 4, and then we just multiply it by 2. You're using that every time you do something like that, okay? I'm going to use that here because one of the constants I could use is 1. What if I had this? It wouldn't really do anything to the value, and that's important because I'm multiplying by 1. But notice what I'm going to do. Because of the property we just looked at, I could rewrite that c over c as c times 1 over c. Right? Yeah. And if I wanted, I could just take out one of those factors. Right? Could do that. So guess what I'm going to do? I'm going to multiply by 1. I'm going to multiply by 3 over 3. But the numerator I'm going to put in here, and the denominator I'm going to put out here.
Isn't that what we were doing before?
Well, the whole reason we were doing that, okay,
You know how to do it now.
well, is because when there was a linear function in here, it would have been a dx was our du, and 1 over a had to go on the outside. Rather than rewriting everything and doing this whole process, it worked exactly the same way every time, so we just learned the rule. Okay? But notice what's happening here. This is why that rule works. Okay? So notice now I have du, the whole thing. I do have a 1/3 outside the integral, but that's okay. I'll handle that at the end. Now I'm just taking 1/3 of the integral of u to the negative 1/2. Okay?
Where did you get? Oh.
All right? So, if you don't have du, look for a way that you can get du. If du were a 10x squared, I'd multiply by a 10 on the inside and a 1/10 on the outside. Okay? Whatever I needed, I would just multiply by that on the inside and multiply by the reciprocal on the outside. Now, what you cannot do is, let's say that it was x cubed dx. I can't multiply by an x on the inside and a 1/x on the outside. That doesn't work. Alright, so we would have something else that we would have to do with that function. Those are the types that we do in AP Calculus that we're not going to mess with here. Okay? So, at this point, all I've got to do is that integral of u to the negative 1/2, so it's u to the positive 1/2, divided by a half, which is times 2. And then I substitute back in for u. So it's 2/3 square root of u was x cubed plus 5. And then I throw in my plus c.
Not too bad.
Okay? It's not too bad. Once you get the hang of it, the process, it will go quickly. But you just have to kind of get the hang of it. Any questions?
No.
Alright, we learn by doing, so let's try some.